Okay, what about asymmetric centers in cycloalkanes? Well, cycloalkanes with two substituents, let's consider those, two substituents. Let's consider this. You could have no asymmetric centers, no enantiomers. You could have two asymmetric centers and have four stereoisomers, or you could have two asymmetric centers but only three. And what does that tell you? There's a mesoform. So look at this first case. 1-bromo, 3-methyl cyclobutane. Now, are there chiral centers here? No, there are no chiral centers. Another term for that is asymmetric centers. If you look at these two carbons here, that's where you might look at and say, oh, maybe those are chiral centers, but they're not, because the four groups, there are not four different groups. If we go around the ring, like from this one here, if you go around the ring this way, around that way, it's the same description. CH2, CH with a methyl, CH2, and back to the original, both paths. So there are no asymmetric centers, no enantiomers, but we do have stereoisomers. Remember, we could have cis or trans. You can see the two versions are cis or trans. So when you have, we figured out that there's no achiral centers by going around the ring two directions. Another way is if you have a mirror plane that goes through the potential chiral centers, that makes them not actually chiral centers. That's another way to identify that they're not chiral centers. Here we have a molecule with two chiral centers, and there is no internal mirror plane. No internal mirror plane. So we actually have four stereoisomers. There are two cis stereoisomers and two trans. And if you build these, you will find that they are not the same. If you build the two different cis molecules, you cannot take one and rotate it around and get the other one. So there are two cis molecules that are enantiomers and two trans molecules that are not enantiomers. Any cis and any trans would be diastereomers to one another. Four stereoisomers, two pairs of enantiomers. Any one of the cis and any one of the trans are diastereomers of one another. Two asymmetric centers and four stereoisomers with another example. Here we have a bromo and a methyl on the ring, but in different location now. Different size ring as well, 6-membered ring. But once again, no internal mirror plane, so we get two cis enantiomers and two trans enantiomers. The third possibility is two asymmetric centers, but only three stereoisomers. And we saw this before. If you have less than the maximum, what does that tell you? You have a mesoform. So we have two chiral centers here, right? Two chiral centers. So 2 to the n, 2 to the 2 is 4. We have the possibility of 4 stereoisomers, but we only have 3 because of the mesoform. And which one is the mesoform? It's the cis. If you look here, there is a mirror plane through the middle of the molecule when you have the cis version, and that makes it meso. Here's another example. You get a meso structure with the cis, but not so with the trans. So look for 4 groups on each asymmetric center that are the same. That gives you an internal mirror plane. If you have one asymmetric center, you have a pair of enantiomers. Multiple asymmetric centers, 2 to the n maximum stereoisomers. And we look specifically at two asymmetric centers, two chiral centers. You have two pairs of enantiomers if the four groups are not the same. One pair of enantiomer and one meso if four groups on each center are the same. And in rings, the meso form is the cis form. The trans form would be the pair of enantiomers.